So, we will continue our derivation for the relation for zone refining. So, here is the plot that we were discussing last time, and this was with respect to zone refining. So, we saw that this is we said this is we are assuming that this is the concentration of a crystal that is shown over here, and then in zone refining you are using the fact that the solute that forms during solidification has concentration less than that of the liquid. And so, taking that concept further, what we do is solidification in a very limited zone. So, this length we are looking at is only L. So, this is a different zone which is in liquid state. L stands for the length here, and here this uppercase L that I am writing is for the liquid state. This is solid state, and this is also in solid state. So, originally this solid overall had a concentration C naught, like I have said here, and when we do the start the solidification, then this there is a curvature somewhere over here. Curvature means there is a distribution, redistribution of the solutes, and the solute concentration has come down. So, somewhere over here, let us say this has this concentration which we can say Cs, and taking the interface equilibrium, the corresponding concentration of liquid is Cl. Now, to find the relation for what will the plot look like, the new concentration plot will look like, what we will do is use a similar concept that we used for deriving Schell's equation. So, this is the solute, let us say this is the additional amount of liquid that is solidifying. So, this is the distance dx that has solidified, and therefore, this amount of solute will get taken away from here, because you see the solute concentration was at this point earlier, and then after solidification it will reach here. So, this is the solute concentration, or this is the total amount, not solute concentration, the total amount solute that will be moved away. And where will it go? The liquid concentration will increase by a delta amount, that is dCl. So, this liquid concentration has increased. So, we will use this fact to set up the equation. So, let us write down how the equation should look like. Cs is a variable, Cl is a variable, but they are related. So, C naught minus Cs times dx is this total amount of solute, and on the right side we have RHS, we have dCl into not dl, actually it is L, dCl into L. So, this is the dCl region and this is the L region. So, now we have a equation over here, and what we will do is we will also invoke the relation that Cs by Cl is equal to K implies dCl is equal to 1 over K dCs, and we will replace dCl by this quantity 1 over K dCs. So, we will have a equation like this. Or we can make it L over K dCs. Now, let us put K over L on this side times dx is equal to dCs by C naught minus Cs. Now, when we integrate it, this becomes Kx by L in a range, we will describe the range, and this becomes minus ln C naught minus Cs and the range. So, what are the range? X moves from 0 to some value x. So, this x goes from 0 to x, and in the same period what happens to Cs? It moves from Kc naught. You remember the first solid that forms is of concentration Kc naught. So, it moves from concentration Kc naught to some concentration Cs. Then we can take the minus sign over here, and I will not write any more over there. I will write the final equation that we should get over here, which will be so starting from this equation, if you solve it and using the limits that distance goes from 0 to x, concentration of Cs goes from Kc naught to Cs, this is the equation you will get. Or to simplify it further, or to put it put Cs on the LHS, you will get Cs equal to C naught minus now what do you see over here? We see that Cs is equal to C naught minus some quantity, everything here is positive. So the concentration of the solid part is less than C naught, but it cannot of course happen throughout the length, but this equation from what we see that it will happen throughout the length. Why? That is because we have excluded the in a final transient zone. So let me to describe it, let me draw the plot in red. So let us say this is during the process. After the process, how would this plot look like? This would look like something like this. It is all less than C naught. So see, this is the concentration of solid starting from x equal to 0 to some value of x, and if we go by this relation, it should keep going below C naught. But at some particular point, the concentration of the liquid will no more be C naught, or it will or basically there will not be enough liquid, and all the solutes will have reached that particular concentration. So it will start to solidify over here, and this would probably be concentration Ce. So we are not talking of this part in this equation. So this equation is limited only up to this point. So whenever we write an equation, you should also be aware of what are the limits up to which it is being used, and in this case this equation is being used only up to this point, and we can clearly see that the concentration of solid, the resolidified solid, is lower than that of the original concentration. Now this is just for one pass. Now let us say you get some another concentration or average concentration from this, which is obviously less than C naught. So if next time you do it, you will get concentration even lower than that. So that way, if you keep doing one pass, you reach C naught minus some delta C1 equal to C prime. Second pass, you may reach C prime minus delta C2 equal to C double prime, and so on. So you see, if you keep increasing the number of passes, your concentration is decreasing far below the C naught value, and this is how you get the refinement or purification of the metal that you are using. And the K value that we have used over here is, if you this over here we have assumed that it is complete diffusion and there is no convection, but what we can also do is we can have some amount of convection, in which case we will have to use the K effective value. And remember one thing that I did not explicitly mention about the K effective, but let me put it over here. When you are growing a single crystal of limited length, then we know that for only diffusion when only diffusion is taking place in the liquid, this is how the concentration profile looks like for the solid. And if you keep increasing the amount of convection, what happens to this plot? That is where the K effective becomes very useful, which I did not explicitly mention earlier, but let me show it now. I am drawing this Z kind of or this zigzag to show that the concentration increases sharply over there and probably it is out of scale. If you increase the if the K effective is even different, you may get something like this. You may see that something, I am just putting some off the tip of the tongue some values. These are not meant to be taken literally, these are just to give you an idea what means when we are changing from complete diffusion to some amount of convection. So let us say the K value, the actual K value was 0.3. When you have very high amount of convection, the K prime may reach equal to K equal to 0.3. So if the depending on what is the K effective value, you may get different kind of distribution or the solute concentration plot. So this is again you can see one more thing from here regarding zone refinement, that when your original distribution is like this and if you use the same condition, your new concentration will become smaller and smaller. So for example, this one was K C naught, this is K prime C naught, for this K prime C naught, and your concentration gets the solute concentration in the solid becomes lower and lower. So that is all of the plane front solidification in single phase alloy. Now what we will do is we will quickly take a look at one example to get a better feel for this. So let us go to the slide, and what you see over here is a problem that is given with respect to plane front solidification. What it says is that a rod of aluminum 2% copper, meaning aluminum is the main content, copper is your the added ingredient. So basically on the left side you will have aluminum and you have added 2% copper alloy is normally solidified under the condition of no diffusion in solid and full mixing in liquid. It is given that melting temperature of aluminum is 660 degrees Celsius, TE is equal to 548 C, maximum solubility of copper in aluminum is given and eutectic composition is given. So what you are given is that there is no diffusion in solid and full mixing in liquid. So no diffusion in solid is something that we have always been considering, and the second condition it says is that full mixing in liquid, meaning there is no concentration gradient in the liquid. So let us to get a feel of it, let us draw how this plot should look like. So you are given some C naught, that C naught is 2% copper. So here you have aluminum, C naught is equal to 2% copper. You are given CSM, you are given CE. Now if you are given CSM and CE, you should be able to find K, which is the partition ratio. So we can get K equal to CSM by CE, which is 33. So it comes to 0.171, and we also know C naught. So C naught is 2%, so let us put it in fraction, so it becomes 0.02, or if you put it in, or if you want to just use fraction percentage, that is also okay. So here we will be using percentage, so it becomes 0.171 into 2 is equal to 0.342. So your Kc naught value is this, and now let us look at what are the things that we need to find. So let us get back to the slide. Now these are the conditions that we are given, so we have plotted it and now we have a feel of it. Now let us look at what the question asks us to do. Draw the schematic of the effective solidus on phase diagram. Well, we have already done that. Also draw the schematic of variation of CS, solute composition, as a function of solidification length fraction Fs. So this part is also easy. Now what it asks, next part is the more important. Also obtain the values and show on the plot important parameters, Kc naught, the concentration of first formed solid, C naught, the equilibrium concentration, and there are different fractions it wants. F1s, fraction where concentration becomes larger than C naught, F2s, where fraction of length becomes where concentration reaches CSM, and it should be F3s, fraction where concentration reaches CE. So we need to find fractions and put it on the concentration versus length plot. So this is how first we will draw just in a schematic way how it should look like. This is this is fraction F equal to 1, C naught we know is equal to 2%, this is Kc naught which is equal to 0.342%. This is where what has been described as Fs1. This is the point, this is Fs1 because it is at this point that the concentration of solute increases beyond C naught. Fs2 is the point where it reaches CSM. So this is CSM, which was given as 5.65. So we have to find a concentration for this. Then we have to also find the concentration where it reaches CE. So this is CE equal to 33%. So the fraction corresponding to this is Fs3. Now we have according to the question we have drawn the schematic for the phase diagram, we have drawn the schematic for the concentration profile. What we need to do now is just find values of Fs1, Fs2 and Fs3. So let us start with Fs1. What is the equation that we will use over here? We will use the Shales equation because it is the Shales equation that is valid when you have no solid diffusion and complete homogenization in liquid. So let us write the equation, which is what we need here is Fs. We know Cs for that particular Fs and other values are constant. So for Fs1, what is Cs? For Fs1, Cs is equal to C naught. So we will put Cs equal to C naught. So we are trying to find Fs1 over here. So this is C naught. And therefore you can take this becomes 1 over k . So you have to just put in the values. This is, and to be consistent, let me put Fs1 over here. So these are the Fs1 values, and when you put in the k values, you would get 0.881. So this is Fs1. Now next what we wanted is Fs2, the point where concentration reaches CSM. What is CSM? CSM is given as 5.65%. So we will use again the same equation. Now instead of Cs equal to C naught, we will put Cs equal to CSM, which is 5.65. So we will put like this. this is FS2. So don't get confused that it is a square, it is just FS2, superscript 2 represents the second fraction that we are trying to calculate here. So I will write over here. Now when you put the values, you would see that FS2 would come out equal to 0.966. So we have FS1, we have FS2, and these are the values. Now what about FS3? So do you think we should also do the same thing? Now if we want to get the concentration FS3 for CSM, should we put it like CE equal to KC naught? Would that be the right way? Well, we said earlier there is a limit up to which this Shell's equation can be applied, and what is that limit? That limit is this point, the CSM value, because the rest of it at that particular point in liquid state, and that point at that point in time or the point in temperature when the solid reaches this concentration, the liquid reaches this concentration. So both of them solidify simultaneously, and therefore what you see, or the fraction at which you see CSM, it is the same fraction at which the liquid solidifies, and therefore FS2 would be equal to FS3, and this equation is not valid for finding the fraction at which concentration reaches CE, and therefore this equation or this plot we can just simply now write the values. FS1 is 0.881, FS2 is 0.966, and Fs is equal to FS3. So these are the different values of Fs, and we have also solved it completely, and we have found all the fractions that were needed. Now there is still another part in the question which says what fraction of the ingot is within plus minus 5% of the average concentration, which means we have to find what is the delta Fs that lies, if this is C naught. Let me use a different chalk for this to emphasize. So we can say this is 0.95 C naught, and this is 1.05 C naught. So this question, this part of the question is saying what fraction of the overall solid lies within this composition, because overall composition was C naught. So we want to know if some delta amount of fraction is lying within that C naught fraction, and what is that delta amount of the length or the fraction. So here is your C naught, and this is the solute concentration, so which is continuously changing. Therefore what we need to find here is this Fs and this Fs. Let's call it Fs prime and let's call it Fs double prime. And what is the concentration at Fs prime? The concentration at Fs prime is 0.95 C naught. The concentration at Fs double prime is 1.05 C naught. So let's again use Shell's equation. So, this is Fs prime, sorry, we have put 1.05, so it is Fs double prime. So, this is the relation to get you Fs double prime, and you can get the value of Fs double prime as now. Similarly, instead of 1.05 we could have put 0.95. And we will get a value of point Fs prime, which is equal to 0.874. So, the difference between these two is the fraction that lies within this. Fraction wise it is 0.014, which means 1.4% of the crystal that has solidified lies within plus minus 5% of the overall alloy composition C naught. So, you see it is a very small fraction that lies within this C naught value. So, this is a very interesting information that although the overall composition is C naught, but the composition which lies within this plus minus 5% of the overall composition is a very small fraction. Most of it lies outside, and in fact most of it lies below it, and beyond this Fs, the value that we found over here 0.966, you see values higher than CSM. So, at that point you are getting something like a eutectic. So, this is again another important aspect is that 0.966 is the value at which you reached the CSM, or the solute concentration at the leftmost point of the liquidus, leftmost point of the eutectic, and that is also the point where you reached the liquid reached the eutectic. So, around 0.034 fraction of the solid has eutectic composition, which means that you have a very even in this very small composition you are able to reach thus eutectic composition. So, that is again to show that even though you may have a single phase alloy with very minor concentration of the solute, you may still reach a eutectic composition and a two phase region. So, with that we will end today's lecture, and we will come back into the next lecture with the second part, which is the cellular solidification. So, this was all we had about the planar solidification in single phase alloy. Now, next we will get into cellular solidification of single phase alloys. We are still with the single phase alloys, but for the cellular solidification. See you in the next lecture.